Modern computers at their core are electrical circuits. A very simple circuit might consist of a battery connected to a switch, then a light bulb, then back to the negative terminal of the battery. Modern computer components typically supply a voltage of 3.3 or 5 volts between the positive terminal and the ground, or negative terminal if you like to think of it that way. Computers treat information as binary, on or off, true or false, 1 or 0, based on if the voltage is high or low. The important component in our circuit here is the push switch, which comes in two flavors. Push to make, that's when a person presses down and the circuit is completed between the two terminals and the bulb lights up. The push to break switch is exactly the opposite. This is the symbol for a transistor. More specifically, it's a metal oxide semiconductor field effect transistor, or MOSFET. Its source and drain are like the two terminals of a switch, but it has a third terminal called a gate. Just like switches, there are two types. The N-channel type makes a circuit when a high voltage is applied to the gate, like a push to make. The P-channel breaks the circuit when a high voltage is applied, like a push to break. So transistors act like switches, except instead of a person pressing it down, a voltage is applied. In modern computers, these types of transistors are used in pairs, referred to as CMOS, or complementary metal oxide semiconductor. The gate terminals of a given pair are always connected together, so they receive the same input. Here is a simple example. If we apply a high voltage, or 1, to the input, the N-channel MOSFET opens a route between high voltage and the output. The P-channel closes the route to ground. If we apply a low voltage or 0 at the input, the P-channel opens a path to ground. Okay, so this circuit seems pointless. We got the same thing at the output as we did at the input. But let's swap around the two MOSFETs. Now, when we apply a high voltage, or 1, to the input, the N-type opens a route to low voltage, or 0. When we apply a 0 to the input, we get a 1 at the output. Whatever we put in at the input, we get the opposite at the output. Later, we will come back to how this forms the basis of all modern processors. Understand that it is vast networks of CMOS pairs like these which allow computers to think. For now, let's see how transistor networks are made in basic terms. Silicon is a semiconductor with 4 valence electrons, which is doped or mixed with other elements. Gallium, for example, has 3 valence electrons, one less than silicon, hence more positive, or p-type. Meanwhile, an element like arsenic has 5 valence electrons, one more than silicon, therefore adding a negative charge, hence n-type. Trace amounts of these elements, typically 1 for every million silicon atoms or so, are implanted by chemical diffusion or by firing them out of a particle accelerator. Transistors are made by sandwiching a region of one of the dopants between 2 of the other. Let's look more closely at the N-channel configuration. This by itself does not conduct electricity, but when an electric field is applied to it, a conducting channel forms, hence the name field effect transistor. This can be thought of in simple terms as the electric field attracting electrons from the N-doped region, which has a surplus, to the P-doped region, which has a deficit. Near the semiconductor stack, we have a conducting electrical terminal. When it's at high voltage, an electric field forms and the transistor conducts. But, to stop a short circuit, we need to add an insulating layer between them. The contact is metal, the insulator is silicon oxide, and finally we have the doped semiconductor, hence the term MOSFET. Finally, the billions of transistors are assembled and connected together by this method. There may be 3 CMOS pairs with 3 different inputs, then going out to 4 different CMOS pairs somewhere else, and so on and so on. To summarize, computers handle information as 1s and 0s, when voltage in an electrical circuit is either high or low. Transistors act as electronic switches, changing between these two states. The transistors always come in complementary pairs, so when one half of the pair opens, the other closes. Lithography is the process by which huge numbers of interconnected transistors are built up on a block of silicon.